Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the teachers and co-founders here. As you can see today, we have prepared a new Biology 1 lesson. I know it's been a long time in the coming, but we're going to be finally putting a bow on the Atoms, Bonding, and Molecules mini-series, which had 3 episodes. You can find the previous episode, which was part 2, linked in the description box below. I highly recommend you watch all 3 of these videos so that you get a basic understanding of chemistry, because when we get into organic macromolecules and we talk about how add elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, how they bond to make these macromolecules, we're going to be using a lot of chemistry related terms, and it's best you familiarize yourself with those. Again, we wouldn't be going in as much depth as perhaps a honors chemistry class or an AP chemistry class might go, but you still need to know basic things, such as parts of the atom, how atoms bond, how the periodic table works, and things like that. Particularly in this lesson, we're going to be looking at energy levels of atoms. We're going to be introducing you all to isotopes and ions, which are types of atoms. And then finally, we're going to be interpreting some basic trends on the periodic table. Again, you would go into more depth about all these things in a chemistry class, but you need a basic understanding, like I said, before we get into organic macromolecules. So before we start this video, I would really appreciate it if you all could like the video, subscribe to the channel, hit the post notification bell, drop a comment down below, and share using our socials. Okay, so the first topic we're going to talk about is the electron cloud. And you might be wondering, what is the electron cloud? So the electron cloud basically is the area around the nucleus in which an electron travels and could possibly be. So we all know that the nucleus is the densest part of the atom. It is the center of the atom where you will find particles such as protons and neutrons, which are the 2 densest of all 3 subatomic particles. Then, in areas surrounding the nucleus, you will find electrons, which are much, much smaller. I believe they're 1,800 times smaller than a proton. Much smaller, but they are very negatively charged. So they will be orbiting, if you want to think of it like comets, like they'll be orbiting very quickly around this nucleus. And the electron cloud is pretty much just proposed area. So if this is my nucleus, the electron cloud would be this area around it in which you could find electrons orbiting around the nucleus. Remember, because electrons have a negative charge and the nucleus has a positive charge because of the protons, opposite charges attract. So electrons will be attracted to the nucleus, so they'll just be orbiting around this nucleus rather than just drifting off into space. So the electron cloud is just that area around the nucleus in which you could find an electron. There are 2 models that were proposed. The first is the Bohr model. The Bohr model is right here, is right where my laser is. So as you can see, here is your nucleus. The red plus signs, those are your protons. The green are your neutrons that have no charge. And then around here, you see these rings, if you want to think of it that way. And in these rings, you see these electrons, and this would be your electron orbits. So the Bohr model has electrons located in circular orbitals around the nucleus. For example, this is a circular orbital, so this is one orbital right here, and this outermost one, this is another orbital right here. So the Bohr model pretty much says that there are circular orbitals around the nucleus where these electrons are located. Each orbital has a quantum number, so that pretty much means so quantum number is known as like n. So for example, the first orbital would be the one closest to the nucleus, which is this one. So this would be n equals 1. That would be this orbital's quantum number. Then the next orbital will be n equals 2 because it's the second orbital, and so forth. So each orbital will have a quantum number depending on its distance from the nucleus. And then this model also proposes that electrons can jump from one orbital to orbital by emitting or absorbing energy. So the orbitals each have different amounts of energy. So if a electron gains energy, it will jump to the next orbital. If it loses energy, it will go backwards in orbital. So electrons are able to gravitate and they're able to move. They're not stuck in these orbitals. And that also will come into play when we look at the outermost shell of an atom. When you see these valence electrons, so those are the outermost electrons, and they are responsible for the way that one atom bonds to another atom, because these electrons are able to jump from orbitals or even share between orbitals. Just things like that. And I forgot to mention this, but the Bohr model, if you're more interested in like the history behind it, it was proposed by Niels Bohr with assistance from Ernest Rutherford. Um, and now we're going to look at the electron cloud model, which is right over here. So the electron cloud model was proposed by Schrodinger. He came up with, instead of orbitals, so think of it almost exactly the same as the Bohr model, in that you have the nucleus in the center consisting of neutrons and protons, and around this nucleus you have electrons. But instead of these circular orbitals going around the nucleus, Schrodinger proposed that you had this shaded area, or this cloudy region, called the electron cloud. So instead of having very, very defined orbitals, like I have one circle here around the nucleus, one shell here, and the electrons are located in this shell. I have a second shell here, and there's electrons located in this shell. That would be your Bohr model. But the electron cloud model proposes that electrons can be found anywhere in this cloud region around the nucleus. So it's just that, if you can see here, we don't really it's kind of like blurry in a sense. You don't have defined orbitals like here. We actually have these rings drawn around the nucleus. So it's pretty much proposing, if you want to think of mist or fog or a cloud, you don't have defined shapes. So it's just proposing that in anywhere in this orange area, you have a probability of finding an electron. So that's the electron cloud model. So those are the two models. So let's talk about electrons and energy levels. So we have different energy levels. Like we were saying before, electrons can jump from energy level to energy level, either by absorbing energy, so becoming even more, getting even more energy, or emitting energy, meaning losing energy. So they will drop they will drop energy levels, or they will go up energy levels. So your lowest energy level will be your innermost one. So if you want to think of it this way, if this is the nucleus, that innermost shell, that's considered what you could call it your lowest energy level. It's the one closest to the nucleus. And the reason you call it that is because you want to think of each electron as having potential energy. So that is the amount of energy, like if you think of it potential, so how much it could possibly do if it's put into action. So obviously, if you have more electrons, you will have more potential energy. So because this innermost energy level can only hold 2 electrons in its outer orbital, it has the lowest potential energy because it can hold the least amount of electrons out of all the other energy levels. Then you move to your second energy level, which is your outermost energy level. It can hold just 8 electrons in its outer orbital. And then you have your third energy level, which is your outermost electron shell, and it can hold a maximum of 18 electrons in its outer orbital. I know this might be a bit confusing, but just this is all you need to understand, that there are different orbitals, and then the amount of energy that the orbital has depends on the amount of electrons in that orbital. It's really actually much more complicated than this, because I'm in chemistry this year actually, and we studied electrons and orbitals in depth. Not only do you have energy levels, but you have sublevels where you talk about different kinds of sublevels. For example, the S sublevel, the P sublevel, the D sublevel, the F sublevel, and each of these sublevels has its own amount of electrons and has its own shape. So, for example, the P sublevel, I believe it's shaped like a pair of dumbbells. Like they have these different shapes and configurations, but again, you don't need to go into that much depth. All you need to understand is what I said before. And lastly, this is just for any of you who are interested, but to calculate the maximum amount of electrons that can be held, you can use this formula. You can do 2 times the energy level squared. For example, if we did the first energy level to find out how many maximum electrons it can hold, you substitute 1 in for energy level, square that, which is 1 times 2, which is 2, which we set up here. If you do the second energy level, 2 squared is 4, 4 times 2 is 8, which we said here. And if you do the third energy level, 3 squared is 9, 9 times 2 is 18. So that would be like finding your maximum capacity. Here you see a little chart that I cropped and put here. This just shows you, I think it says follow the yellow brick road, but it just shows you the progress of energy levels. For example, if you start up here, 1s, the 1s sublevel, which I was talking about, was going to be an S sublevel. So an S sublevel can hold 2 electrons, and it's in your first energy level. And if you progress to the next one, you move to your second energy level, because remember, your first energy level can only have 2 electrons, and that will be found in your S sublevel in your lowest energy level. Then you go to your second energy level, which is represented by the 2. Second energy level has an S sublevel as well, and that holds 2 electrons. The thing is, your second energy level can hold a maximum of 8 electrons. Therefore, in your second sublevel, you have in your second energy level, you would have another sublevel called your P sublevel. And the P sublevel can hold 6 electrons. So 6 plus 2 would equal 8. And you just follow this. I'm not going to go into as much depth because I'm pretty sure you're confused by what I just said. But you'll learn all about this in chemistry. You do a whole chapter on it. But that was just a basic overview of energy levels. So let's just look at this basic diagram of one oxygen atom to better understand energy levels. So right here we have the nucleus. You see the protons in the nucleus. These like yellow circles, they have a positive charge. The protons are represented by the plus signs. The neutrons are represented by the yellow circles. I'm losing my mind. I'm saying one thing and I'm thinking one thing and saying another. But yes, the protons are the blue plus signs. They're in the nucleus. They have a positive charge. The neutrons are the yellow circles. They're also found in the nucleus with the protons, and they have a neutral charge, meaning they have they have no charge at all. So often you'll see this written as 0 with a line through it to indicate there's no charge. It's just neutral. Here you'll see around the nucleus these red minus signs. They're electrons. They're in the electron cloud or the orbitals, and they have a negative charge. Again, this is the nucleus. This is going to be your first energy level here, this first ring. It can hold 2 electrons. So as you can see, we have 1 electron right here, this minus sign here, and then we have another one over here, another minus sign. Here we have our outermost energy level. So as you move through the periodic table, atoms will have different amount of energy levels. So in this case, oxygen has 2 energy levels. So that's why 2 are shown. It's not that every single atom will have 2 energy levels. Some might have 1, some might have 3, some might have even more. So this is just showing you an oxygen atom. That's why they particularly said oxygen atom. And then moving on, the outer energy level, this has a maximum of 2 energy levels. So in the second energy level, you will find 6 electrons. So these would be your valence electrons, because they're your outermost electrons. They're responsible for any of the bonds that this oxygen atom will engage in. And then if you add these 6 in the outermost energy level with the 2 in the innermost energy level, you get 8 electrons. And oxygen's atomic number, which we'll be talking about, is 8. And as you can see, there are also 8 protons in the nucleus. So these kind of balance each other out, make this a neutral atom, because if you have 8 plus charge and then 8 minus charge, if you add those together, it's like 8 minus 8. So if you have 8, and then you add negative 8, and then you'll end up getting 8 minus 8, and you'll get 0. So that's why it's a neutral atom. Typically, you'll find oxygen like this. And let's talk more about this concept of atomic mass, atomic number, and so forth. So let's first talk about atomic mass. So atomic mass is the number of protons in the nucleus along with the number of neutrons in the nucleus. So if you want to think of it in other words, as I wrote here, the total number of particles in the nucleus. So if you want to think of it this way, how large is the nucleus? How much space does the atom take up? How large is the atom? So that would pretty much be your atomic mass. Obviously, the more protons and neutrons we have, the larger the atom is going to be, because the more space it takes up, the more mass it has, meaning the more matter it has, meaning the more space it'll take up. So the atomic mass, if you ever see, like, for example, oxygen, if we say here, your atomic mass is measured in atomic mass units, that's what AMU stands for. Those are the units we use, just like you use inches for length or pounds for weight, you would use AMU for atomic mass. It says 15.999. Sometimes, like, for example, the periodic table I use in class, it says 16.00. It just depends. So oxygen is always in that ballpark of around 16 atomic mass units. So this represents the total mass of the protons in that atom plus the total mass of the neutrons in that atom. We don't include the electrons, obviously, because they are so small that their mass is insignificant. So it really does not add anything to the atomic mass of an atom. So here you will see the atomic mass pretty much represents the combined amount of neutrons and protons in the nucleus of the atom. Moving on, the atomic number. The atomic number is the number of protons in the atom. So it's the number of protons. So the number of protons, in other words, so atomic number and the number of protons are literally interchangeable words because atomic number equals number of protons. And this number will define an element. And I'll explain why. Before bonding, the atom has an equal number of electrons and protons, meaning it's neutral. So I'll explain all of that. So again, I have that same picture from the last slide. You see the atomic mass units measured in AMU down here, 15.999. So this is the sum of the amount of neutrons and protons in the atom. Up here, and remember, this block that you see here, it's literally taken directly from the periodic table. So if you've ever seen a periodic table, in my first video, I actually showed you all a periodic table. You will see blocks like this on the periodic table, and elements will be in each one of these like blocks, if you want to think of it that way. That's why I wanted to take this exact image. So it's literally like we pulled the oxygen block out of the periodic table and we're analyzing it now. So the atomic number, which you find up here, we see that it's 8. So you're going to find the atomic number at the top, which is going to be this number. It's always going to be a whole number. So in this case, it's 8. And this atomic number, like we said up here, represents the number of protons in the atom. So, like I said, this represents the amount of protons that you will find in the atom. So, for example, in oxygen, you will find 8 protons. And like I said, number of protons and atomic number are interchangeable terms. If I say the atomic number is 8, you will immediately know that the number of protons in that atom is 8. And the reason I say this defines an element is because no matter what chemical reaction occurs, the number of protons will not change in an atom unless you intend for it to change. And the moment you change the number of protons in an atom, that atom becomes a different kind of atom. For example, hydrogen on the periodic table has 1 proton. If it undergoes a chemical reaction where a second proton is added to the nucleus, it's no longer hydrogen. It's now helium because helium's atomic mass number is 2. So just like that, if we change for example, if we removed or added protons to oxygen, it would become a different atom. It'd no longer be oxygen. And again, before bonding, the atom has an equal number of electrons and protons, which means it's neutral. So you can assume that all of the elements on the periodic table are electrically neutral, meaning the amount of protons will cancel out the amount of electrons. So for example, if we know that the atomic number is 8 for oxygen, we know that the amount of protons oxygen has is 8, but we also know that the amount of electrons oxygen has is also 8 because they need to balance each other out. So if we have 8 plus charge, we need 8 minus charge so that we have an electrically neutral, so the net charge is 0 in that atom. So let's talk about atomic mass and number and the relationship between the two. So to find out the number of neutrons in an atom, what you want to do is you want to subtract the mass number from the subtract the atomic number from the mass number. The reason this makes sense is because we said the atomic mass number in AMU is the amount of protons plus the amount of neutrons in an electron, and the atomic number is the amount of just protons in the atom. So if we want to find the amount of neutrons, we have to subtract the total amount of protons and neutrons. We need to subtract the protons from that so we can isolate the amount of neutrons and find out the amount of neutrons. So in this case, if we rounded 15.999 up to 16 and we subtracted 8 from that, we can say that the amount of neutrons in the atom are 8 neutrons. So as the atomic number of an atom increases, the atomic mass of an atom also increases. So for example, if we're adding more protons and neutrons, obviously the atomic number will increase as well because the amount of protons is going to increase. So they have a relationship in which they will increase together. And in other words, the more subatomic particles in the nucleus, the larger, denser, heavy the atom. So subatomic particles in this case would be the protons and neutrons. We're not including the electrons because their mass is insignificant. The more we have of those, obviously the larger, denser, or heavier the atom is going to be. So the more space, more mass it's going to have. Now let's talk about isotopes. So like we said before, we're going to introduce you to isotopes and ions, which are like cousins of like our regular atoms that we find on the periodic table. So isotopes are atoms of the same element that have different numbers of neutrons, and we'll talk about this. So example 1 would be oxygen 16 and oxygen 18. So the way you would explain this is in that last slide we were talking about, we had an oxygen atom that had an atomic mass of 16. Meaning, when we subtracted 16, the atomic mass, when we subtracted the atomic number, which was 8, which is the amount of protons, we found the amount of neutrons, just the amount of neutrons, which is also 8. And that makes sense. If we have 8 neutrons and we have 8 protons, if we add them together, we get 16 total subatomic particles in the nucleus, and our atomic mass number is 16 atomic mass units. So that matches up. So in a normal oxygen atom, you're going to have 8 protons and you're going to have 8 protons and 8 neutrons. And if it's electrically neutral, you'll have 8 electrons as well. So that's why it says in example 1, oxygen 16. And oxygen 16 is pretty much you're adding the protons to the neutrons and you're getting 16. So that's a normal oxygen atom. But then we also have oxygen atoms called oxygen 18. So oxygen 18, if you think of it this way, it's still an oxygen atom. And if it's an oxygen atom, it must have 8 protons. So if we subtract 8 from 18, we get 10. And what does 10 represent? Well, 10 represents the amount of neutrons that are in the nucleus. So we've added 2 more neutrons. So this is an isotope of oxygen. So oxygen 16 and oxygen 18 are isotopes because oxygen 16 has 8 neutrons, but oxygen 18 has 10 neutrons. However, they're both types of oxygen because they both still have 8 protons. The second example that's very, very common, you will see this used in like radioactive dating for organisms. We'll be talking about that later on as well. Is carbon-12, which is stable. So carbon's atomic mass is 12, so it's stable. But then you have carbon-14, which is radioactive. So carbon-14 has 2 more neutrons than carbon-12. So if this is stable, if you add 2 more neutrons, you kind of make it unstable. So this is radioactive. So if we just want to think of it exactly how he did the oxygen 16, oxygen 18 example. And here's another example in a picture that might help those of you who are visual learners. So here's hydrogen 1, which is your typical hydrogen atom. You have 1 proton, 1 electron. You don't have any neutrons. The mass number is 1 because we only have one subatomic particle in the nucleus. And again, this is the electron shell, like this yellowish area. Then we have hydrogen 2, and we call this deuterium. It's just because hydrogen 2 is common, it's like commonly used to explain these concepts. It has its own name, it's deuterium. Its mass number is 2 because look, we've added a neutron to the nucleus. So now we have 1 plus 1, so now we have 2 atomic mass units in this atom, which is an isotope. And then we even have hydrogen 3, which is tritium. It has 2 neutrons, not just 1. We've given this hydrogen atom 2. So now if we add 1 plus 1 plus 1, we get 3 subatomic particles in the nucleus. So now the mass number is 3 atomic mass units. So these would all be isotopes of hydrogen because they have different amounts of neutrons in their nucleus. Now let's talk about ions. So ions are charged atoms that have gained or lost electrons. Remember how we said before that an atom was electrically neutral because it would have the same amount of protons as it had electrons. For example, an electrically neutral oxygen atom that had 8 protons would also have 8 electrons, so those charges canceled each other out to give you a net charge of 0. However, we have instances where we have ions where we have charged atoms. So charged atoms have gained or lost electrons. For example, we have a cation, which is a positive ion. So to make an atom positive, you have to lose electrons. For example, if we had an oxygen, actually, I think the best example would be showing you over here. So the cation right here is your positive ion. If you see this polar molecule, um, if you see this polar molecule, you see that it has negative charges on a negative charge and a positive charge. So this obviously polar molecules, we'll talk about that later on, but they have they're little they have partial charges, but a cation is pretty much what happens here. I think the best example would be this NaCl. So sodium and chlorine react to give you your table salt, NaCl. What happens is sodium will give up one of its electrons, so it is a cation. It loses an electron in its shell, gives it up to chlorine, and it becomes Na plus. So it becomes positively charged because now it has more protons than electrons because it lost that one electron. So now it's not balanced. So now it has more positive charge. If we look on the flip side at an anion is a negative ion. So if we look here, chlorine has seven electrons in its outermost shell. Since it's gaining an extra electron and the amount of protons is not changing, it's becoming even more electronegative. It's gaining more electrons. So at this point, the amount of electrons is more than the amount of protons in this atom. So it's going to have more of a negative charge. It's not going to be at zero anymore. So the only way you can form ions without changing the element is by getting rid of or gaining electrons. You cannot get rid of or gain protons because if you do that, you're going to change the actual element, which is what we talked about previously. So those are the two types of ions. Now let's talk briefly about the periodic table. So here's one of the trends almost that I wanted to talk about was the octet rule. So all elements on the periodic table want to achieve the configuration of noble gases. So the the noble gas is going to be that last column that you see on the table. That last group that you see on the table, group 18. They include helium, neon, argon, krypton, xenon, radon, and so forth. So that last group you see are the noble gases. They're all colorless, odorless gases, but they're special because their outermost energy level is filled with 8 electrons, except helium, which is a special case. It has 2 electrons, but because it only has 1 energy level, it's fine. It's happy with 2 electrons. All these other ones, such as neon, argon, krypton, xenon, and so forth, their outermost energy level has 8 electrons. So the outermost energy level for them is completely filled, meaning the atom is stable, so they don't want to react. They don't need to, because the main reason atoms will react is to become more stable, and the way they become more stable is by filling that outermost energy level with its maximum capacity of electrons. So that's what octet rule means. So all these atoms are striving to be like the noble gases. They're trying to get those 8 electrons in their outermost energy level. So octet means 8. So by doing that, they become stable. They don't need to react. They don't need to gain more electrons. They don't need to lose more electrons, so forth. So we'll briefly just talk about that here continued. So all atoms are electrically neutral before they react, meaning the amount of protons will balance the amount of electrons, so it has a net zero charge. The noble gases are just like this. They are electrically neutral, but on top of that, they're also stable, and they don't want to react no matter what because they are inert, because they have a full outer shell, so they don't need to react because they don't need to fill up their shell. They don't need to get rid of electrons. They have the happy number, if you want to think of it that way. They don't need to change anything about themselves. They're happy the way they are. So all atoms are unstable and want to react to obtain or lose electrons to get in the configuration of noble gases, like we said before. For example, hydrogen has 1 electron in its outermost shell. It'll want to gain another electron so that it can have the same configuration as helium, which has 2 electrons in its outermost shell, and it's stable. So that's an example. So for another example, chlorine, like you saw on 2 slides ago, has 7 electrons in its outermost shell. It wants to gain 1 more so it can have 8, and it's really looking for that last electron to fill its shell. And this applies to every single atom on the periodic table. They have varying degrees of electronegativity. For example, atoms like lithium that have one electron in their outermost shells, they will want to give up that electron so that they can get rid of that shell, and then the shell inside that has 8 electrons. So all of these atoms have different ways of trying to get rid of or gain electrons so that they have that stable configuration. This applies to all atoms except the noble gases, which are already stable. And bonds are formed to give, accept, or share electrons, fill the outer shell, and have stability. And I think this is a perfect segue into the next video. So again, we're going to have bonds where atoms will be giving up their electrons to other atoms, where other atoms will be accepting electrons from atoms, where atoms will be sharing electrons, not essentially giving them up, but just sharing them, maybe not equally, but still sharing them. They all want to fill the outer shell because this, again, will lead to stability. They can become inert. They don't need to react. They don't need to search for that missing key in their puzzle, if you want to think of it, a missing piece in their puzzle. So that's all I have for you today. I hope you enjoyed the video, and please look out for the next Biology 1 video. I believe it's going to be more on focusing on bonding, specifically ionic and covalent bonding. If you like this video, please like and subscribe to our channel, hit the post notification bell, share using our socials, and drop a comment down below. Please visit our website and email us at our Gmail if you would like to. Stay tuned, and you'll be getting another video very soon. Bye.